Well, it's a pleasure to be in this conference, and I have to apologize not being here in person, but some unexpected events prevented me to come, so I'm very sorry for that, and Hubert. Okay, so, well, let me start again. So, as I said, for these quantum integrable models, we have a lot of aims, starting from constructing them, solving them through various indexes or separation of variable, whatever. And finally, computing form factors, correlation functions, spectral functions, and getting some numbers that we eventually could compare to some experiments. And usually when I say that in such a talk, I have some nice picture which goes back to some work we did with Jean-Sébastien about spectral functions in the Heisenberg chain. But because it is Hubert's birthday conference, I remember that Hubert is fan of some comics and that he was using them 4 years ago in some analogous conference in Lyon. And so I did not resist for picturing some cartoons. And this is well-known comics with Roadrunner, which is a high-speed bird, right? Very high speed, and this poor coyote is just running after. And sometimes you can think it has some philosophical meaning for us. Okay, so let's go to the topic of this talk anyway. So this talk is about really a basic ingredient that we all know in the integrable settings, which is complete set of commuting conserved charges. So the word complete has a precise meaning in classical case, where we have this Liouville-Arnold theorem. And although in practice, separation of variable is essential to get up to the solution in general. But in quantum case, we have no analog of this. However, Sklianin invented in very long ago now, quantum separation of variable scheme, and he was able to, using Young-Baxter algebra, to design such a scheme which helps to solve, at least in rank one case, a lot of models. And in fact, what is very interesting is that using this method, you somehow go out of the ansatz framework. You have really a resolution. Okay, what I would like to say in my seminar to present is a new approach to this separation of variable, and in particular, how to construct a basis of the physical Hilbert space, which presents the properties of separation of variable. And such bases, they are not constructed as in Sklianin setup from some B operator, A operator, and so on, but just from the knowledge of a complete set of conserved charges and the knowledge of their commutative Bethe algebra, and in particular, the knowledge of the corresponding structure constants. And I have to say that all what I will present in this talk is based on a series of work with Giuliano Nicoli and more recently with Louis Vignoli, which is our student. So outline is, I will try to present you what are those separation of variable bases obtained from, say, transfer matrices in various cases, in particular in GLN cases. Then I will show you how it works in the usual case, where Sklianin method also applies for rank one case. And then I will go to one example of higher rank, simplest one, GL3, and show you that there you can go quite far and eventually consider the first steps to the dynamics by considering scalar products. Okay, so let me just remind you what we mean by separation of variable bases in the quantum setting. So let's consider you have a one parameter family, for example, transfer matrix family, T lambda of commuting charges acting on some finite dimensional Hilbert space. And suppose you can design some basis of the dual parameterized by some discrete coordinates, y1, yn. They are discrete because you are in the finite infinite dimensions here. And such that, first, it is a basis. And second, any eigenvector, common eigenvector of the family T lambda, has a wave function which is factorized in terms of some function qt, depending only on one variable. And such that these functions, they are solution of some discrete difference equation of some order dn in the yn only, so one variable equations, while supplemented in general by some proper boundary conditions. Well, then, of course, you see that you go from the simply n variable situation to one variable. And of course, this is a big simplification. But of course, you are not happy just with that. Usually, if you want to prove that you have a complete spectrum, you need to further have as a possibility to describe explicitly the T lambda, the T lambda action on such a basis. And in fact, if you are able to do that, then you can prove that conversely, if you have solution of this secular equation, say, in the variable yn, then you can go back and prove that you have completeness and that you can construct eigenvectors. Okay, this is very reminiscent of the classical, of course, Hamilton-Jacobi situation. So the question I would like to address in this seminar is really how to construct separate bases from transfer matrices in quantum integrable systems, and such that you have all this scheme complete. Okay, well, of course, separation of variable has a long history in quantum integrable models, as I said, starting with Krianin, where he invented these very nice tools and applied them to Toda model in particular. And since then, this has been applied to a lot of other models and by a lot of people, extended. And I would say that in the rank 1 situation, it's very successful. But for high rank, of course, some problem arises. And these problems have been addressed in the recent year, starting from interesting conjecture from Nikolai Gromov and collaborator, some proof of the conjectures, and some extension of them by Dima Volin and collaborators again, and even more recently, some other works by this group. And the key new element in this game is, I think, the framework we developed for this separation of variable basis with Giuliano Nicoli in 2018, and this is what I would like to describe. So let me just show how this basis can be constructed from transfer matrices. Well, first of all, if you have, let me define what I call basis generating family of conserved charges T lambda. So suppose you have such a family such that there exists a covector L, okay, this covector L here in H star, and some set of conserved charges T, H, I, which are constructed from your family T lambda in some way. It could be powers, it could be evaluation in some point, it could be fusion, well, whatever. You will see several examples in the following, such that when you consider this set here, H1, Hn, where you apply the product of your conserved charges for various values of HA, which are ranging from 0 to di minus 1, and the product of dn's is just the dimension, total dimension of your Hilbert space, then this is a basis. Okay, so if you have such a situation, I would say that you have a family that can be used to, that is basis generated. And in fact, in all known quantum integrable lattice models that we have been considering so far, we succeeded to construct such things. For example, if you take GLN in the just fundamental representations, then you see that if you take just, if you have a lattice with inhomogeneities, psi1, psi-n in the lattice sites from A from 1 to n, and if you take evaluation of the transfer matrix in those points, and provided you have taken some quasi-periodic boundary conditions given by some matrix K, which has simple spectrum, then you can prove that, for example, this is the basis of your Hilbert space. Okay. So suppose you have proven that, and I will show several examples. What are the direct consequences? Well, the first consequence is that if you take any eigenvector T of your family, commuting family of transfer matrices, T lambda, so hence it is an eigenvector also of your object THAA here. Well, if you take the wave function in these coordinates, it is separated. So you have a trivial constant here, and you get here a product of functions which are just the eigenvalues, and you see that it is pure product of functions of individual coordinates HA. So you have separation. Well, if you have such a separation, immediate consequence also is that any eigenvector is determined by its eigenvalues. So it means that necessarily the spectrum, the common spectrum of your conserved charges, T lambda, is simple. Okay? Whenever you fix the eigenvalue, you fix the eigenvector up to some trivial constant. So this is very interesting because if you have simple spectrum, then you should think a bit about what are consequences for matrices having simple spectrum. So this is for Hubert again. You have to look for instructions. Well, so let's go for instructions from elementary linear algebra. So if you have a simple spectrum matrix, X, D cross D dimensions, then you can write its characteristic polynomial, its degree D polynomial. And then you can introduce what is called the companion matrix. And the companion matrix, it is made out of many zeros, just ones above the diagonal. And then the last row, you get just coefficients, A0, A1, and so on, with minus sign, which are just the coefficients of the characteristic polynomial. And then immediately what you can show is that the canonical basis, left basis for such a matrix, is just given by taking the first vector E1, applying C to the K for K equals 0, 1, and D minus 1, and this generates just the canonical basis. So you generate the basis by just applying powers of the companion matrix on one vector. So if you go back to the original base for X matrix, so you take EJ times Vx, right? And then you find out that there exists a vector F1, which is just E1 times Vx, such that if you apply X to the K for K equals 0, 1 to D minus 1, this forms a basis of your space. So if you have a simple spectrum matrix, it means you can generate a basis of your space, using just powers of this matrix. And so it means also that in that basis, coordinates of any eigenvector, lambda, big lambda, of your matrix X, as coordinates given by the powers of its eigenvalue. And in fact, it's even better, well, obviously, if you take any vector, lambda, which is written in terms of small lambda, which is an eigenvalue, so a solution of the characteristic polynomial equation, then you can prove it is an eigenvector because you have the basis Fn, the covector basis. So the only thing you need to prove is you take coordinates of this kind, you apply the matrix X on lambda, if lambda is non-zero, of course, and then, unstable connection, I hope you still hear me. Okay, so, and what you can prove immediately is that to prove that it is an eigenvector, you project on the basis. So if n is less than d minus 1, it's directly, you see, you have to compute fn x lambda. You apply not to the right, because this is what you want to prove, but to the left, you get fn plus 1. So you get lambda to the n, and you prove this equation. The only case which is slightly more complicated is if n is d, because fd, action of x on fd, is x to the d. It goes out of the basis. It's not a basis vector. It stops. Basis vector are for up to the power d minus 1. But now we know that the matrix x solves its characteristic polynomial. So you can re-express x to the d in terms of lower powers of x. And so you can just prove that you can act with xd by using these lower powers. You get a sum over an lambda n. But this sum, because lambda solves the characteristic polynomial, it's an eigenvalue by definition. You know it is lambda to the d, and so you prove your result. And in fact, what is very important here for the rest of the talk is that if you consider the vector space Cx of matrices that are commuting with X, it has exactly dimension D as a vector space. And its basis could be taken as just the powers x to the k of the initial matrix X for k from 0 to D minus 1, which means that any matrix commuting with X can be decomposed linearly on that basis. And moreover, if you look at the basis vectors of C of X, which are the x to the k, you can compute they form a commutative algebra. It's not only a vector space, it's a commutative algebra, because the product of two matrices commuting with X is still a matrix commuting with X. You can compute the structure constants of this algebra just from the coefficients of the characteristic polynomial. Okay, and I have to mention that there is related recent works by Dima Volin and collaborators about studying. Okay, so this is linear algebra. So let me go back to the SOV basis for transfer matrices. So if I go back to my simply a basis, suppose I have such a basis with some TAHA, which is a basis of H star. Then because it is a basis, it means it's a free system of vectors. And if it is a free system of vectors, it implies immediately that the set TH, which is just the product of the TAHA for any HA, it is also a free system, but then of operators. In the vector space CT lambda of matrices of operators commuting with T lambda. But this has dimension, because T lambda is simple spectrum, has dimension the Hubert space, which is also the dimension, the number of operators in such a set. So it means that this set is also the basis of the Bethe algebra CT lambda. Okay. But CT lambda is not only, of course, as Cx, just in the what I showed just before, is not just a vector space, it's also an algebra, a commutative algebra. So if you multiply two conserved charges commuting with T lambda, they are still commuting with T lambda, so they can be decomposed linearly on the basis. So there exist complex numbers like CH H prime lambda or CH H prime H double prime, such that TH T lambda can be decomposed linearly on the basis and TH TH prime also. And so these relations, they, first of all, enables for the computation of the action of T lambda on such basis. That's the first point. Second point, such relations, they hold for operators, so they hold also for their common eigenvectors, and in particular, if you apply on eigenvectors, they hold for eigenvalues. And in fact, in all cases we looked at, they just fully characterize a complete transfer matrix spectrum. So these relations usually, and I will show in examples, they are just direct consequences of fusion relations satisfied by transfer matrices, and also they are equivalent in general to some quantum spectral curve equation. I would like to say that there is a very nice link to Kolya-Reshetikhin idea of analytic Bethe ansatz, because of course, such relations, TH, T lambda, or TH, TH prime, they are valid at the operator level, and they are valid for the eigenvalues. So there are constraint equations for the eigenvalues. But here it's no longer an ansatz. And the reason it's no longer an ansatz is because we know the action of the transfer matrix T lambda on that basis. And if we know that, then we can go back and prove that if you have solution to those constraint equations satisfying proper boundary conditions, then they are giving rise to really true eigenvectors. So the key question in this game, in fact, is what is the optimal choice for the set of conserved charges? So you see, because we have the choice, we just need that we pick up some sets that's such that you get a basis, right? But there is many ways in general to do that. Not only one, not just eigenbasis of B operator like in Slianin way. Here we have the choice of conserved charges. So it's a key question to ask, what is the optimal choice? And the optimal choice is not only for spectrum characterization, it could be also when we go to scalar products and computation of form factors, correlation functions, and so on. Well, for rank one case, I will try to show that it is related to Baxter Q operator choice as an object generating the basis. And for high rank cases, I will show that it is slightly more involved, but I will comment on that a bit later. And I want to mention, as I said, recent work by Dima Volin and collaborators studying Bethe algebras. And I think this is a topic that we should continue because studying Bethe algebra is very important and studying possible basis is very important. Okay, so this is a way, Hubert, that you can look at what are SOV bases, and you know that from the cartoons that you should be careful when you consider such apparatus. Okay, so for GLN case, as I said, if you go to fundamental representations, and if you go to arbitrary, there is other formulas, but if you just take fundamental representation, which was in our original paper in 2018, you take R matrix, which is combination of permutation and identity. You take a twist, which is arbitrary. This is GLN and invariance here, so you can put arbitrary twist. You take the transfer matrix to be just the trace of your monodromy matrix, satisfying the Baxter algebra. And then what you can prove immediately that you can construct indeed such a basis, taking some covector L that I will describe, times the product of the powers just of the transfer matrix itself. So the HA, they go from 0 to n minus 1 in that case, and you evaluate the transfer matrix in the psi A, and the only thing you have to make sure is that K, here, the twist that you put in the definition, it has simple spectrum. So if it has simple spectrum, you can prove that this is a basis. And moreover, you can take for L just a pure tensor product, and the vector LA, that should be just such that when you act with K inside A to the power H, with H running from 0 to n minus 1, this produces a basis. But this is, just the simple spectrum condition on the K matrix. Moreover, if K is diagonalizable with simple spectrum, then you can prove that T lambda has the same property. Okay. So let's go for GL2 and see concretely what it means. So consider spin S. Well, we did it for spin 1/2 first, but you can consider spin S. And then you can prove that you have a basis which is just generated by some products of fused transfer matrices evaluated in shifted points. So psi n are still the inhomogeneity parameters. There should be in generic positions. And you can choose some covector O here in some specific way, such that this is a basis. So K1 and K2 are the eigenvalues of your twist matrix K. I will suppose here, but you can go to more general cases that K1 is different from K2 and that they are both non-zero. And in any case, K is different from the identity. While fused matrices, they are computed recursively from the fusion relations. Delta here is the quantum determinant. It can be computed explicitly in terms of the function A and D and the eigenvalues of K. And the one thing we proved is that first of all, this basis computed like this just coincides with Klianin separation of variable basis computed from the B operator in that case, when it exists, because it does not exist for all possible K where our scheme applied, but when it exists, for a special choice of the covector O, which is just reference vector 0 in this chain. So the vector where you have maximum spin, or the converse. And what is very interesting and very important for the full characterization of the spectrum is that if you look at this basis, you can just using fusion relation, you can show that the transfer matrix action in the chosen point here can be just obtained as a linear combination of only two vectors. So shifted plus and shifted minus of the one coordinate. And remember, because in such models, Tk is a polynomial of degree big N, using Lagrange interpolations plus asymptotic behavior of T lambda, you can get a full action of T lambda just knowing this Lagrange decomposition in the chosen points. And so you have a linear action, which is essential for proving that you have a full spectrum. And in fact, we proved that spectrum is complete in the sense that if you take any T lambda in the set of polynomials having specific asymptotic value in terms of trace of K, and in terms of some set of parameter XA, which are solution of just the set of n equations fused to Sn plus 1, evaluated in psi n to Sn equals 0. You see those polynomials, they are just functions of the unknown x1, xn. So you get high order 2 Sn plus 1 equations. Eigenvector should satisfy this equation here, but conversely, any here with a specific asymptotic value give an eigenvector. And in fact, you can prove even better that this is all equivalent to the existence of a Q operator, satisfying just the well-known TQ relation, here written explicitly in terms of the K1 and the functions A and D. And that's even better. The basis can be written just fully in terms of Q operator. You change slightly the covector L here. Can be obtained from the covector O that I showed before, and just the product of Q in the shifted points. And you get from this a clear understanding of the linear action of Tk on the basis, because you see TQ relation is very nice. It says that TQ is just Q shifted plus and Q shifted minus, so it's linear in Q. And so when you act, if the basis is generated like here by Q operator, then acting with T on that basis is a linear action. Okay, so let's see what it gives for high rank. Well, for high rank, situation is slightly changed. So let me go just to fundamental representation. You have fusion identity here. So there is two levels. So you have a T1 and a T2. T2 is constructed by an antisymmetrizer. And of course, a full antisymmetrizer gives a quantum determinant. And you have a two-level fusion equations. So T1 gives T2, and T2 gives quantum determinant in specific points. And then you can just use this scheme. I'm probably running slightly out of time, so let me show the result. So you can characterize fully the spectrum using just these two levels fusion relations, supplemented with the asymptotic value of the polynomial T1 in terms, again, of the unknown x1, xn, satisfying just the Q determinant relation. And because you know how to act back with the transfer matrix on your basis, which is this just the basis I showed before. Okay, so the basis which is given just here with powers. In the case of GL3, it's 0, 1, and 2 here. Okay. Then you can prove that your spectrum is complete, and moreover that the wave function they factor in terms of the eigenvalue in that case. And this is the way it works is very similar, although more complicated, as in GL2 and as in the linear algebra for the matrix X I showed. Okay, so far so good. And then you can show even that you have a quantum spectral curve equation. So you prove from the equivalence to the fusion relations for the eigenvalues that there exists a polynomial of that type satisfying just now slightly more complicated equation, which is written here. And moreover, you can show that the wave function, they factor in terms of these Q functions. Okay, well, there is much more to be said on these higher rank models, but I would like to touch about some other subject, which is scalar products. I don't know how much time I have, but probably I started at past 10, so probably I still have a few minutes, but okay, not much, probably. So if you want to consider scalar products, which are essential tools to compute form factors and correlation functions, then you have to introduce two bases, left and right. So in the GL3 fundamental representation, you can just define them like this. So you see, instead of powers, you take T2 and T1, but T2 is a kind of inverse of T1. So it's very close. In fact, you can show this is equivalent in most cases to the previous basis. And then you can start computing scalar products. So we did that with Giuliano Nicoli and Louis Vignoli, and we found, well, quite some formula. So the formula, the matrix of scalar products starts very well with some normalization here that is given below, some Kronecker delta, so this is very nice, orthogonality like in GL2, but then you see you have a series of non-diagonal terms. This series still is well ordered in terms of powers of the determinant of K, the twist matrix, and you see you have some coefficients here, CK, CHK, which are defined recursively, and some selection rules here. So this matrix looks interesting. There is related results by these gentlemen, and they used that even to try not exactly the same formula. They have different representation, but well, I believe it should be possible to prove equivalence. But you see, I have no doubt that you can use, and we did several computations to compute some form factors with that, and even some to try to look at correlation functions. No doubt that such formula can be used, and that the fact that the scalar product is not the matrix of scalar products, and hence the SOV measure, which is just the inverse matrix to that, can be used to effective computations. But somehow my feeling is that this could end in sufferings. You know, well, cartoons like it's like, you know, it's like this, that somehow non-orthogonal SOV basis, it's not so nice somehow. You could have some drawbacks. So we decided that we should make advantage of our vision of SOV basis from conserved charges. So maybe if you get such non-orthogonality, it means that you did not pick up the right charges to construct the basis. You see, there is many choices. And so what we were able to do is to define new charges, making advantage that we have a simple spectrum transfer matrix. You can define them in the eigenbasis of this transfer matrix in some specific way. And the specific way is to remark that when you look at the scalar product formula here, it is well ordered in terms of determinant of K. So suppose you take a simple spectrum K, for example, diagonal, K1, K2, K3, and K3 is 0. So the determinant would be 0, and hence you would have orthogonal basis. So suppose you have this for K, some K hat. So you know you have fusion relations, which simplifies and so on. And then you build up a new operator in the eigenbasis of the full transfer matrix Tk, where K is your general K matrix, K1, K2, K3, for not K3, K3 is not 0 here, but you put eigenvalues which are coming from K hat. Well, this is still a matrix which is commuting, which are commuting among themselves and which are commuting with the transfer matrices of the original twist K. But then you can construct orthogonal SOV basis just with this new T fat. And in fact, the scalar products are very nice. And if you use such basis, then you can prove that you get very nice determinant representation for scalar products of separate states with eigenstates, which goes like such a formula here, where you have just pure determinants which are computed in terms of the functions alpha and the functions t here, which appear in the decomposition. So the only question here, and I will just drop the other models, although they are nice, to the results and questions. The main question here is how to get more algebraic construction of those optimal SOV bases, in particular having orthogonality property. I think this is very important, and probably it's related to the extension of the notion of Q operator in those general models, higher rank models, because if I just showed TQ relation in this GL3 model, you notice that you have still T1 times Q, which is like in GL2 case, but you see you get a term which is T2 times Q. So TQ relation is not linear. TQ relation is not linear. You don't get linear action of T on Q. And so this is a major problem, I think, and this is what produces non-orthogonality. Okay, I have to stop there. And of course, as a gift, Hubert, I noticed that you have nice glasses, not like mine. I mean, just rectangular ones. So I was curious, and I did some deep research, and I found some very nice picture. You see, it seems that with your glasses, something can be achieved, really. So let me okay, change myself. Okay, and well, yeah, it looks much better, it seems, that way. Well, you know, maybe this is just a dream, of course, but this dream makes this coyote very happy. So I would like to wish you to continue to dream and eventually to catch some of your dreams. And I wish you a very happy birthday, Hubert. Thank you. Thank you.
Okay, thank you very much. Do we have questions?
So do you have questions?
Yeah, hello, Jean-Michel, that's Hubert. Yeah,
hello, Hubert.
I should tell people it's a long-standing joke, because once I compared Jean-Michel to the coyote and and the roadrunner to the XXZ model, but or XXX should I say? But finally, you've caught it, so I'm happy. And I'm happy I taught you to like the coyote at least. So very nice talk. How about quantum field theory? Can we think of using the ideas in this context?
Well, I did not try. But you see, I hope that, well, you know, this is quite fresh somehow. We try to do things with this new basis built out of conserved charges. I think they are very nice, and probably we should try for quantum field theory case. Well, probably it's more complicated to prove that indeed you can construct bases there, but why not? I think it's very You know, so many questions already for lattice cases where you have everything under control, that I would like to understand how to construct nicer bases, really. So bases in particular, this T-fat that I showed for GL3, we know that it exists because we have the eigenbasis and so on. So we know that it exists, we know the properties, but we don't know how to construct them algebraically from the start, from the T lambda somehow. You know, not just going to the eigenbasis of T lambda, but in general, some more simple construction. So this is not easy. And I think that before going to quantum fields, which is very important, very interesting question, I would like to settle some of the basic questions here. But well, you know, if Jean-Bernard is right, that after 60, we are 60 more years, well, maybe we can try to do something.
Okay, any other question? Okay, so thank you, Jean-Michel, and Vincent as well. Thank you very much for the talks.
Thank you.